Right, with effects of dielectric on capacitance of the capacitor. Effects of dielectric on the capacitance of the capacitor. We need to be fast because church people will be here like around 4. So, is it 2? Effects of dielectric on the capacitance of the capacitor. So let's be fast. Effects of dielectric on the capacitance of the capacitor. We know that in our last class we said that dielectric simply has to do with that insulator or insulating material, which can be air or any insulator, placed in between the plates of a capacitor in order to increase capacitance, then reduce what's it called? Spark. We said a lot about dielectric in our last class. So today we are doing effect of dielectric on capacitance of a capacitor. So if you remember, dielectric test, when we did Q equals to C, do you remember this formula? Yeah. And I told you that this one is a constant, right? So that means initially it's supposed to be just this, not. So please, for effect of dielectric on capacitance of the capacitor, we are going to look at its effect on charge, then its effect on voltage. So if we look at that, we solve some questions from your textbook. Then we now go for our next class. So please, what did I say? I said that when the dielectric is air, Q will be equal to, C itself will be equal to what? There's something I said that time. I said that first of all, C will not be equal to K, C naught. That is the one without air, the one with dielectric will be equal to constant. Then the capacitance that is with air. If you remember, that's what I told you in our last class. I told you the reason is that if it's with air, you not say this is 1 times this is the same thing. You say that capacitance of dielectric is equal to that of air. But if it's not so, that's capacitance, there's a dielectric inside. This constant will no longer be 1. It's only 1 when the game is only 1 when the dielectric is air. I said it. So if I know that, it simply means that this particular equation, which is K equals to CV, K equals to Q, equals to CV. If it has to do with air, Q should be equals to Q on N with a C naught V naught. Why? That is when the dielectric is air. That's what I mean. Why? When the dielectric is with a dielectric that is not air, it will just be equals to C. So if I know that, it simply means that I can call this equation 1, equation 2, and this junction equates these two things. So that I now have that C naught. Okay, let me use this time. We use the one with dielectric since we did this thing. So I now have CV equals to C naught V naught. That is dielectric with air. Or dielectric when it's air. When air is in the medium, when air is the dielectric, and when there is a dielectric that is not air. Equals to this. But please recall that these two have a relationship, capacitance that has dielectric and the one without dielectric. That is with air has relationship, which gives you that C is equal to K C naught. So I can place this here. I can place this here with this value. So that I have K C naught. Then I have V is equal to C naught V naught. We need to be fast on this. So if I have this, you can now very well see that there is something common between the two. What is that? So that I now have making V solid of the formula. Anything you want to make solid of the formula, no problem. But the essence is simply, if you remember that relationship, charge and voltage, and it causes electric field to be created. That electric allows electric field to be created, but it doesn't conduct. We did all this thing in our last time. So this is not the same thing as saying KV equals to V. Making this subject of the formula you have equals to. So what we are trying to use this to establish is that voltage cannot pass through dielectric. So as dielectric is increasing, voltage is decreasing. If you remember that time I showed you capacitance in series, I told you that if you come here and you come here, that is for parallel number. But when it's series, it simply means that it will want to get here, and there's still another capacitance here, and it can't cross it. And I told you it's more like a gallop. I said it. So work, voltage is decreased by dielectric. That's what I'm trying to say. But capacitance is increased by dielectric. That is why if you check this thing, C here is directly proportional to AC naught. Is it not? It's a direct relationship. But notice here, it's an inverse relationship. So note that. Note that. I believe the essence of stories, when you go here, you read it, then go through the notes and the explanations today in our Saturday class, because that's where we normally have time to explain this lesson. And tomorrow, by the grace of God, even if not tomorrow, Friday, I'll make sure that I teach you on Friday, so that I'll still take time to teach this more, so that Saturday we do direct electricity. I can clean it, right? What to be fast? So this one is for voltage. There's a situation where that is we used, remember we started the whole thing with charge, is it not true? We started the whole setup with charge, Q. I told you that relationship for capacitance is Q, parallel plate Q, charge directly proportional to voltage. Why capacitance is the constant? So now let's use when voltage is the subject formula. We started with making Q subject formula. Then we now use the things here to equate. Now let's start with how to make this subject formula. V is given by this formula, ER. Always remember, we've said it over and over, that whenever you're getting voltage, that we use ER. We have different formulas for this, so within the one that has to be over this and that's E over C. But in an electric field, V is equals to ER. Now let's say that this V equals to ER is the one with dielectric. Now when the dielectric is air, when the dielectric is air or vacuum, air or vacuum as dielectric is this case. It will now be V naught equals to E naught R. Noting that I did not put R out because the distance of separation is constant. Do you still remember? Okay. We've done this Saturday class, so please, I don't want to repeat the ones we've done that day. So see, if I equate these two things now, see, I'll now have ER. See now, see. I'll now have ER equals to E naught R. But see, before I equate this, check, this is the normal thing I should do, right? Or please notice something. This V here is equals to something here. Is it not good? Chevy? So before I do this E naught, that will be hungry us to rush and do. Before I do that, I will say that V that is here, V here that is equals to ER. This V is equals to V naught over K equals to ER. So if you make this something else out of it, I have V naught equals to K ER. So this is what I can have. This, if you got this equation 1, call this equation 2, then automatically this becomes your equation 3. So what I will now do is to equate these two things, equation 2 and equation 3. So equate equation 2 and equation 3. So that you now have E naught R is equals to K E R. Something is common. Here you see that this thing is common, distance. This can cancel this. So I now see that at this junction, notice that our goal is this K, because that's the dielectric constant. Our goal is to check whether that dielectric constant will have a direct relationship or inverse relationship. That is what we have tell us, okay, this is the action of dielectric here. It's either increasing it or decreasing it. So that is our goal. So if I want to make this subject of formula, because it's having this one K is close, so that's the one I'm making subject of. So this E now will now be equals to this E naught. That is the electric field for the capacitor in air when the dielectric is air all over K. So this is the final answer. So which means that they have an inverse relationship. As the dielectric is increased, the electric field between the two is decreasing. It allows the electric field. But if you have a strong dielectric, it simply means that its ability to conduct will be reducing. So that means the more the dielectric, the lesser or the decrease the electric field we have. But just that it will ensure safety, it will ensure that there is no breakdown. So note that. So the next point I want to touch is what we call dielectric breakdown. Dielectric breakdown, because you see all these things in objective course. If you even check your textbook, you see questions on that. Dielectric breakdown. Let's be fast. Are you there? But I can do it. Right, dielectric breakdown. It is the maximum electric field. It is the maximum electric field. Dielectric breakdown is the maximum electric field. Dielectric breakdown is the maximum electric field a dielectric can allow. The maximum electric field the dielectric, maximum electric field the dielectric can allow, after which it conducts. The maximum electric field the dielectric can allow, after which it conducts. The maximum electric field the dielectric can allow, after which it conducts. So please, what that dielectric breakdown is talking about is simply, it's saying that the breaking point of the dielectric is simply that point where that dielectric can no longer just allow electric field. At that point, it has over-stressed or over-yielded. It will now become a conductor instead of an insulator. And why will it become a conductor? Because we know that naturally, if charge is too much, action of point phenomenon will take place. The air around that region will start conductivity. So that is what the electric breakdown is talking about. You will see it in objective question. They might put it however they want to put it, but that's just what it's talking about. So with that said, let me give you a diagram to illustrate the strength of the electric field of the dielectric plate. The goal is to make sure that we touch everything as possible. Everything we are supposed to touch as much as possible, so that when you see it in objective question, you don't feel like that means you think of one thing. Let's say this is the battery. Let's say this is the negative. From our next class on electric, direct current, and all this stuff, it will become more interesting. But most of these things will be doing it over every day. So let's see. If I have this, notice that negative charge is moving here, Shabby. Do you know why this side positive charge is moving? What do you think will happen to this capacitor? The charge in the store will be in such a rate. There you are. And the charge this one will stop. Now see what will happen. Remember that this is capacitor plates. But inside here, even if it's air, initially, all these things are moving in musical direction. That is, if it's positive, negative, they are scattered. Positive, negative, scattered. Positive, negative, scattered. But the minute you apply this pattern, charging it will go. First of all, do you remember that electric field moves from positive to negative? Now see what will happen. Because you have charged this negative this side, positive this side, there are charges, electrons and protons inside here. What will happen is that the positive one will will be drawn to the negative side. While the negative one will be drawn to the positive side. So what will happen automatically is that inside the dielectric diagram, we now have the positive side close to this. Positive, negative. Inside. There are so many of it, but this is an order to take. From that being random, to just take this order. Now, what will now happen is on this inside, so this will be the setup. This will be the setup. This is the setup of the dielectric. All the charges inside here will quickly be arranged, meaning to charge this in this order. So now see what it has done. That is why it doesn't conduct. That is why it doesn't conduct. Because of the fact that the charges, the electric field is moving in this direction. But on the inside, if you check it, the electric field inside here that it allows this is positive now. Is it not positive? If you look at it, this positive is going this way. So if you check it, moving straight, you see that the electric field inside here, what is inside this direction is moving in this direction. So which means, because of the fact that the flow is not in this order as well, it can't conduct. So it's moving in an opposite order. The electric field is permits the electric field to pass through into an insulator. But the electric field inside on this side is moving in the opposite direction to the actual electric field. So which means it doesn't conduct. So at that point where it can no longer do this, that's the breaking point. We say that it's not dielectric breakdown. In that case, it's no longer resisting this. All of it is now no longer in this order. It's not flowing this way. It cannot conduct as dielectric breakdown. So note this diagram. When they ask you action, they should explain action of dielectric strength. They should do dielectric strength. Whoever is asking you expect you to explain that. It's all dielectric. So with that said, please, I want you to check your, I want to do it. Because I know this is something we have stopped in our Saturday class. So check your physics textbook, chapter 3 question. I want us to see how many of it we can solve for calculation aspect before church people can write. So check. Let's be fast. Any physics textbook? Because when money is go to management block B. You people should have recorded that is this one. As I said block B, that one you are going to, does it have fan? Is it not only this one that has fan? And I said that one has fan. But you've not been to this one before. Well, thank God, sir. Don't want something. So let's be fast. Define capacitance of the capacitor. I know you can do that. Define capacitance of the capacitor. On what factors does its value depend for any particular capacitor? On what value does the capacitor does the capacitance of the capacitor depend? What value? I didn't hear you. People should try and make attempts. On what value does the value of the Area. Yes, sharp, 3, correct. So if you remember when we did capacitance, that time that we came outside, we know that capacitance from Q equals to CV. Then we say that C is equals to Q over V. When I said if you go to, if you use Gauss theory, EA equals to Q naught over E naught. Like Q naught equals to EA E naught. So if you carry this and put here, then V itself is given by ER. So if you put this now, you now have that C is equals to E A E naught all over ER. This will cancel this. So capacitance is simply A E naught over R. So it depends on the area, permittivity of free space, distance of separation. Very important to note. So let's solve C part of N of 1I. And already in my group, in the group video I posted, I told you that whenever the capacitor is in series, that all you just need to do is to do the products divided by the sum. Maybe you saw it. So when it has to do with resistor, we will still get there. When the resistor is in parallel, anything you do for capacitor in series, that is what we do for resistor in parallel. We will still get to that and we'll see the reason. For now, let's go capacitor. So the question says two capacitors of capacitance, two capacitors of capacitance, two capacitors, that's really fast, two capacitors, okay, two circular, you are supposed to be coming here with your textbook. You see, two circular plates. Before you start blaming me, let me first blame you. Two circular plates. Separated. Two circular plates separated a distance 3.4 mm apart. By a thick oil of relative permittivity. When I say very because I will know that relative permittivity is very because 4.8 is used to make a capacitor of capacitance 565 picofarad. Now they said calculate the radius of the plates. Are you following? Yes, number one. So let's solve, let's be fast. Okay, let's be fast. So what you do is you write solution. I've told students, sometimes you don't know a question. The minute you write solution, the answer will be there. Then once you write solution, the next thing you start writing out everything you have in that whole story. You start writing everything out. I want to finish, but I have space. Okay, you can see under the board. No. Why are you there now? You move forward now. Why are you going to the back to that state? You move forward. Are you seeing it now? I am fast. But you see, a good number of a good section of the board will be used because I will not climb up there. And you copy fast. So two circular plates separated the distance 3.4 and then apart dialectic coil of relative permittivity. 4.8 is used to make a capacitor of capacitance 565 picofarad. Calculate the radius of the plate. So what I just need to do is to bring out the distance of separation. So the distance apart, the distance apart, B equals to 3.4 mm. Because this is two circular plates, the area there will be pi r squared. And pi is 3.1429. Now, the r, I don't know it. That is the radius. Okay? Then, the relative permittivity K, which is equals to ER, is equals to dielectric constant, is 4.8. The capacitance was given C is given to the 565 picofarad. And in my last class, I taught you how to get this thing. So pico is what? Stand us for what is pico? Is it 9 or 12? 12. So which one is just power 9? Which one is just power 6? Which one is just power 15? Add 18 double T-O. Which one is just power 18? Minus 18. Femto, Chevy. Please, don't memorize all those things. So I gave it to you in my last. You will make copy and a note. Thank you very much. Don't memorize it too. You are there, Chevy. You are a man. So with that said, I'll now use the formula. The two formulas I have for C. From Q equals to CV, I get C equals to Q over P. And I know that when we compare this electric field, it's also equals to A V naught over R. Should we? Yes. Hope I'm correct? Yes. Well, now let's substitute everything now. So that first of all, it's the R here. This is C equals to pi r squared E naught over R. So I want to make the R squared as something for this is the same as saying CR equals to pi r squared E naught. Define E naught will be going on. Is it not? Hope you. Okay, I'm there. Don't be there. See what I'm saying? I'm saying, before I start putting all these things, is it not true that this A means pi r squared? This one is E naught, and this is R. I just said, try to make the r squared that they say we should find. They say we should find the radius. Try to make the radius of the formula. If you do it, you will see that if you want to do this one times this one, that is what's multiplied. Then you now have this. So if we have that, we now say divide both sides. So see, you divide both sides by, going that R squared is equals to C is equals to 565, Sherry? Yeah? Which one? It cannot cancel it because one is radius, one is distance of separation. The arrow, see what that means. See what that means. If you know that capacitor is like this, when they say circular, it means that the capacitor is the one that looks like this. You can have a capacitor that is like this and another one that is like this. Sometimes you have one that is like this and one that is like this. So if you know that this distance of separation is that distance, the arrow that is here. Why the surface itself, the surface of this capacitor is this the one that has that arrow square, that is from this end to this end, from this end to this end, from this end to this end. That's the way that came about. So if it will confuse you, you will always replace in some textbook you see that this arrow will put it as D. That's for distance. I ask. Somebody got my picture. Okay, let's do it. There's no reason. So this is now, let's go minus 12. Then, arrow that is given to me, what did I tell you is the arrow? 3.4. But this is the same as saying 3.4 times 10 raised to power minus 3 meters. Sure you know. Millimeter to meter is divided by 1,000. So, times 3.4 times 10 raised to power minus 3. All over. Pi is 3.1429 times permittivity of free space is 8.85 times 10 raised to the power minus 12. Look, we are not missing anything. Huh? 4.8. Okay. Why you miss the 4.8 is because at this point you're supposed to do here. Remember that this one, we only use this one when the dielectric is N. Is it not true? Once there is a dielectric given to us, we use this one. Madam, are you with us? So that means that time we started doing our rotating. This here should have been somewhere. Let's say at this point we have this. It's supposed to be somewhere here. That is ER. Then that time that we divide everything that has to do with the coefficient of R squared, the K is supposed to be here too. It's supposed to be here too. Sure you know. And it's supposed to be here. If you like, be confused. If you like, think that you are confused. This thing is not hard now. So the K is always there once a dielectric is given to you. Assuming they do not tell us that dielectric for it is air, I will not bother. So thank you for pointing it out. So that means I'm supposed to have 4.8 times. I have punched for me everything. What they are. None of these are say arrows. It's not supposed to be off. Okay, you see that? Jesus. Thank you. What's the time? Yeah, by this type of time, somehow my brain used to do like that. Punch for me. Thank you. Punch. Like, if possible, you do everything. Don't do the arrow square, we do that after next. One question, you spend 2 hours on one question. You said, I hope we are all following. Wow. No. Chimamaka's going be here. See, when we did dividing now, it's supposed to be at that point where we did dividing. Guys, the K is the 4.8 K for relative permittivity. Dielectric constant. So what we are saying is that this should have been this way. You might use your hand inside the notebook. Write this thing like this. Then convert the area to be like this. Now, since this is what we are looking for, make sure that formula see if we get the same thing now. Watch for me, what we are. That's everything. 0 like this. You did not do the other section. Now, be sure that there is no mistake. So now if you take the square root of both sides, use to cancel this, so that R will be equal to bunch. Please inform them on the group chat that we are here. Management will have post again, so that somebody don't go and sit at MME or stay inside Hobby and say I was looking for you people. Please post for me on the group. Post for me, please. 0. The answer is 0.11. 0.1199. Okay, so R is approximately 0.12. And that's the meter actually, because we used everything to be in SI units. Okay, this 0.12 meter. If you check your option, if the answer is in centimeter, I believe you know how to convert it from meter to centimeter. Like multiply by what? 100. So if you multiply by 100, the answer is in meter. That's what it is. It's in centimeter. Okay, yes. So if you check, the answer here is in centimeter. So in centimeter is represented as 12 centimeter. This semester physics, very simple. Only electricity, only magnetism. Very simple. Number 2 question. 2 capacitors of capacitance, 4 microfarad and 2 microfarad respectively. 2 capacitors of capacitance, 4 microfarad and 2 microfarad respectively, are joined in series with a battery of EMF 100. Do you know what EMF means? Electromotive force. But what did I tell you it is? Well, let me tell you. The difference between electromotive force and voltage is simply that electromotive force is simply the battery, the charge, or whatever it is, that battery, or whatever DC circuit is having when it's not in use. It has the capacity to be used, but when it has not done anything, we normally refer to it as EMF. But when it has done work in a circuit, we refer to it as potential difference. You get the point, sir? Yes. Generally, they are all called voltage, so just know it. Sometimes let's see it and think the electromotive force there is for force. It's still voltage. So with that said, I said 2 will be fast. Capacitors of capacitance, 4 microfarad and 2 microfarad respectively, are joined in series with a battery of EMF 100 volts. Full stop. Connections are broken terminals of the capacitors are then joined. Find the final charge on each capacitor. Oh yeah, be fast. This is the only tutorial center where students learn to solve questions. You say solve and they're kidding. You go around and you solve and they're kidding. Hey. So copy, be fast. It's in tutorial class they impregnate you. Academically. So you know, we are about entering the middle of the day, is it not the when you need to be very careful. Middle of the day, when you need to be very careful. The school is on fire, hope you know. Yeah, when the school is on fire. But yeah, you know that school is on fire. Don't worry. Just be playing. Be playing. Please, if you are a student in this school, be extremely mindful with your activities. Extremely careful. Don't be a stupid student. I know what I'm saying. Don't be a very stupid student. So if you are playing with your life, like with your future, like it might not sound the way it should sound now, but years from now, when you now say, I have calmed down, I now want to be useful. People will now refuse to allow me to be useful. Is it not you that is this person? How can you be useful? Just, please, don't play with yourself too much. I'm telling you. I want to play. But yeah, the first time is to write solution. So I bring out C1 equals to 4 microfarad. I bring out C2 equals to 2 microfarad. In some textbook, you see this thing written as MO. This is how it should be written. MO is for me. So if you know this, now they said are joined in series with a battery of element. So please, I want to clean this part so that I can use the word properly. I will illustrate this. So the first part of that was I told you that full stop is highly important in this semester physics. So the first full stop here, this is what it's talking about. And please, for every full stop you get, don't be the type that you want to do all the full stop at once. This question, the way it's asked, it means that you have to solve the first full stop, finish, before going to the second one. If I try to use common sense to put those things again, the way I want it, I will have issues. So let's solve that first full stop. In series, I told you, what you just do that this voltage, the smaller part is minus, the bigger part is plus. This voltage, if it moves now, let's say this plus come and come here. This minus come and go here. While you now, look at this thing now. Shall you see that it's not hard, like what's voltage normally, but it just goes go here, go here. So by normal setup, there is nothing going here, there is nothing going here. It will need more voltage, means simply the work done moving the unit charge and every charge from one point to the other. So for the fact that it doesn't meet this, another work will be done. Another work will be done. It's not the same work that is done in moving this, that will be done to get this charge here. That is why I said once you notice the setup is this one this way, that means see it as a gallop. So when it's in series, we say that voltage is different. So for another one to be done, yes, we're going to be having this negative and this will be positive. But have it in mind that another work was done in order to get that. It's not the same voltage that move that. It's not the charge you are saying that is voltage. The voltage is moving the charge. So what you now need to know is the charges here are the same because if you check this straight line illustrates line of charge. Straight, they are the same. It's different from when I have one here, one here. So if I know that instead of something to stress myself, doing all those 1 over C and the rest, I just say C net. The total capacitance is simply the same as say just their product, since it's just two capacitance. All over their sum. Again. What if it does not work it out?
What if it was more than 2?
If it's more than 2, you will go through 2 before you get to 3 now. You will go through 2 before you get to 3. So when you go through 2, if there's another one remaining, you can also use the same setup to now join the third one after you've gone through 2. So you remember that initially I gave you something like this, 1 over C net equals 1 over C1 plus 1 over C2 dot that is plus dot 2 1 over Cn of negative. But I'm saying if you don't want to be suffering yourself, then you can do this. So you do 4 times 2 all over 4 plus 2. This is going to be 8 over 2 here. 2 here. So it's just going to be 4 over 3. So Cn says the total capacitance for this series, the total capacitance will be equal to 4 over 3. That's the total capacitance. Now that I'm putting the total capacitance, I want to get the charge. Yes. So they gave me 100 voltage. And remember that the voltage for series is different. Do you remember? Do you remember that when it's series, the voltage is different now? So let's say I want to get the voltage here. Because in order for me to get charge, I said that the charge is the same. So in order for me to get the charge, I need to know out of this 100 voltage, how many is here? How many is here? So let's do it by saying I have Q equals to C, let's do C net, C net, this is the same, this is then just wait for them. Let me do 4 over 10. Let me find charge first. I have watched for me. If I find voltage here and voltage here, I want to find the charge. Charge is the same now. Charge is the same. You find that charge using the total voltage. But the total voltage for here, when you see it will be different. So good for me, because this is equals to what? 400 over 3, which is equal to what? 103.3. And because this is micro column here, micro farad, so that means this will be micro column. People can hear me stress. Come to the front. We'll just look at the PTA meeting. Come to the front. Please, that is for the charge. So we get the charge by knowing that charge is the same. So once we've gotten the total capacitance, we use the total voltage to get our charge. Don't confuse it. If you notice how I normally drag this thing, because I know that some students misplace it. They do many things. So then if I want to get voltage here, that is when this thing is in series. I want to get voltage here when this thing is in series. I can simply do say, okay, if that is the case, what is it? How do I get charge? How do I get capacitance here? It's simply by doing 1/4. Is it not true? And what is here? Simply by doing 1/2. So let's go. I want to do this. It's not part of what we are supposed to do, but I want to do it extra since this is tutorial class, so you know it. Can I get it? So we said that U is the same, then C is supposed to be 1/C plus, but let's do this one. I have C, then I have B1 plus B2, it should give me the V next. Then, if that's the case, maybe this order of the because Q over C. Q over C. So if I have Q over C, and I know that the charge is the same. The charge here is the same. The charge here is the same. Okay. Actually, I can do that. I can do this for me. I can actually do. Yes, I can actually do using this because. I can actually do since the charges are the same. 1.3 all over this one that is here. And then V here equals to this 133.3 over 2. But punch for me, what we have. There are so many ways I can go about this. As I'm looking at it, there are so many ways. See, since the charges are the same, I put. So the capacitance here, I have punched for me the first one. Yes? That's 3.325. The second one. 66.6. Okay. Number C. Assuming I don't know this thing. Let's check if the 2 sum up to 100. Sum the 2 up to 100. Units equals 99.975. Okay. Which is approximately 100. What do you mean? Okay. So please, in case you want to do voltage, guys, you find the voltage of each one. Because if you check it, this thing is set, since it's constant, it's set as 1 over C1. If it's set as 1 over C2. And C2 is 2, C1 is 4. So it's still the same thing that of 1 over C1. So I just want you to know it in case. But that is not what they asked us to find. I just did it for the sake of the fact that this is tutorial class. We've gotten charge here, and the charge here is the same. That charge here is Q equals to, can I get it? We've gotten the total capacitance, and we've got that total capacitance so that we can be able to find the total charge. So now that we've gotten the total charge, we now need to go back to that question and look at it again. So please, what I'm saying in essence is, see, what I'm saying in essence is, whenever you are solving this question, as it has to do with capacitor, resistor, whatever. Any full stop you see, use it, even if you don't know what it is for. Use it to go back and say, what did we say that capacitance is talking about? Capacitor is talking about parallel plate. We said that in a situation whereby the charge is directly proportional to the voltage. Then you now put C as the capacitance. Use it to see if you can find the charge. See if you can find the voltage. See if you can find the capacitance. When you are done with that full stop, you progress. That's just what I'm trying to say. So you don't just go and treat it like GST, you just draw something, then you are now asking yourself, so what do you do, what do you do? Every connection, for every connection, there is charge produced, there is voltage produced, there is capacitance produced. For every connection. So if you hear it was connected in series or parallel and then broken, that connection initially gave birth to charge there. Something charge happened there, something voltage happened there, something of capacitance happened there. Show it. Then you now progress to interpreting the question again. That's what it means. So I want to move to the next part of that question. The B part of that question says the connections are broken. The connections are broken simply means they remove the battery first. That is the first thing about broken. Now, then I said the line terminals. That means even the capacitance itself disengaged, because when something is connected in series, it means this is one part of this capacitor. This is another of this capacitor. So when you come and say this is the head, this is the tail, you can't tell and head and join. That is capacitors in series. Like when they tell you capacitors are connected to like terminals, automatically they are talking about capacitors in parallel. When they say capacitors are connected to like terminals, they are talking about capacitors in series. Note this. So if this is the tail, this is tail, the left hand side, this is the head. So when they tell you capacitors are connected like terminals, automatically what they are telling you is that if you have this thing like this, and you have another one like this is like terminal to this. This is like terminal to this. If these two are connected in such a way that they now move down to join a voltage, that is what we mean by like terminals. So whenever you see a question say they are connected by like terminals, they are just indirectly telling you that those capacitors are connected by parallel. The same way is when they tell you resistors are connected like terminals, they are talking about parallel. Everything capacitor and resistor, the same setup is the same. The only thing that is different is just a formula. And the reason why the formula is different is because from Ohm's law, he quoted it to be voltage directly proportional to the resistance. When you now come and put current there, something will happen. When we get there, you see. But everything I'm teaching you about capacitor, both the setup, everything, is the same way with when resistor is in parallel. The same way with when resistor is in series. Just like the formula, according to Ohm's law, makes the parallel mode to have a different arrangement, which is that of series in resistor with that of parallel and capacitor. Why? That is the formula, not the setup. Setup is the same. So when we get there, we still see it. So just note this one. So with that said, let's continue to interpret the rest of the set. Connections are broken, and the terminals of the and the like terminals. So it means that I will come here and say, okay, I see like terminals are getting about parallel. So you break it, remove the battery. Remove the battery. Connect this so that the like terminals are releasing. They are broken. And like terminals of capacitors are joined. The final touch. But let me, since it's connected, capacitors don't just connect. This is wire. But let's say you don't know the voltage here. Now notice something. Notice something, please. Notice something. This capacitor, they did not say change to. is still 4 microfarad and 2 microfarad. The mistake you will make is looking at capacitors as charge. The charge here, because of this thing, before it happened, the charge is bringing to this place. So this one is 133. And this one is also 133. This side, if we assume this side to be positive, this is 133. On this side, positive, 133 on this side. If we assume this side to be negative, this is 133. Once again, it will be 133. 133. So if we assume that this is positive, this is negative side, this is positive part, what it means is that you carry the capacitors now, you disengage it from being in series, and then put it to be in parallel. And as you put it to be in parallel, what you've done is simply, you've made it in such a way that you are now having 133 on everything on this one. The charge here is different from the charge here. Are you aware? So because the charge here is 133, the one here as well will be 133 because in series they have one charge. So if you are not going to calculate the total charge in this circle, since they said that the right hand has are joined, it simply means the same thing as saying plus of this and plus of this joined. Negative of this and negative of this joined. So if you check it now, the charge on these two now is simply going to be the same as saying 133.33 plus that is these two being joined, then plus 133.33. So the total charge here, this is the units. This is the total charge. The charge on these two, if you join the two, since they said the right terminals are joined, this is the total charge here. This is the total charge. Do you remember when I told you that if charge here is different and charge here is different, do we not let do the total charge? Should we normally do after to do the total charge? So in this case, we already know this one that charge is here and charge is also here. What is the total charge? And simply say the charge here, bring it and add with this one. That is what I was saying. So then I will find the total charge. The total capacitance will simply be in parallel. We don't do one over anything. So it's simply going to be the first one plus the second one. So if you don't want to stress yourself when it has to do with capacitors in parallel, just know that how you do it. If you don't want to believe this thing that I've said, let's take it that this thing is being thinking too much. Let's think in what physics gave us as common. Physics said Q1 for parallel plus Q2 plus Qn gives you total charge. Equals C1 plus C2 plus Cn gives you total capacitance. But you can only have one voltage for parallel. The voltage for parallel can only be one. And notice that the voltage here is not the voltage here. You are aware? You don't know it. Don't make the mistake of going to use it because it was broken. Here you remember. Then you know that it was broken and the voltage got back. So let me just come and put it here. Now, child of God, use your hand now and do it from where. What is the charge 1? The charge 1, what do I have as the first charge? Plus. Why have any other charge? It's just this one. Equals C1, what do I have? The first capacitance is 4 now. Plus 2, showing I don't have any other thing. I now have oh yeah. Multiply, add up. This will give you what? 2.6 equals to, is it 8 or 6? Look where. Here, what this guy there, exam, if that's the outside, is it not? They will not be saying it. You that was shining, you just keep quiet. So please, always pay attention. So divided by 6, divided by 6. So the voltage now will what? 44.4. That is the total voltage. Remember I said, not supposed to have what?
This microfarad.
Remember everything we've been using so far, we've not converted anyone. So if you don't convert, just use your value. So when you get to final answer, if you check option this morning, you can now convert it to something. So this is not converted to anything. So V gave me 44.44 volts. So please, if the only time is really, normally we are supposed to convert, but if you notice that what you are giving here is micro, and they do not give you farad, here is the same. If you use it to the last, it's still going to give you the correct answer, because if you convert your final answer to farad or whatever it is, it's still correct. So then I will go to the final voltage. Notice that the question did not ask us for final voltage. What the question is asking us is final charge on each capacitor. Shall you see? Somebody will then want to ask me, how will you be doing all these things? That is why it looks as if in secondary school this topic is one kind. Because if you are focusing on directly what you are asked, without the concept of knowing that you should be thinking of how do you find charge, find capacitance, find voltage, before looking to see if you can get each of them, you will be having issues. This question that involves capacitor and resistor, does not focus on you answering what you are doing. It focuses on you having the mindset that charge directly proportional to voltage means that you always need to know that every question asked requires you finding the whole charge, the whole voltage, the whole capacitance. Before, if now along the line you're able to solve that what you are asked, you can now stop there. But it's always requiring you to go through the whole thing. So if I'm not going to be finding charge on this, they said I should find the final charge on each capacitor. The final charge on each capacitor. I think I've done that along the line. The final charge on each capacitor, but we'll do it now. Why we're going to be doing the final charge on each capacitor is because of the fact that we now have to show me. Let me know it. Let's check. Let's check. On each capacitor, I got 133.33. I want us to analyze. Let's use our value to analyze to see if we get the same thing. Then we'll be correct. Find the final charge for each capacitor. Okay. On each capacitor. Please remember that this value that we got. Remember this value we got it by doing the capacitors in series. Capacitors in series. Okay. Can I come in? which is 44.44 V. Now, what it will now help me to do is to simply now go to each capacitor, times each capacitance with that V, times each capacitance with that V. That is the total charge exactly on this, due to the fact that I joined two charges, like the light terminals. So the final charges for each one is simply this and this. I hope this is not confusing. Is it confusing? I feel it will confuse you owing to the fact that you are thinking of the charge we carried when we joined the terminals now. But do you remember that charge we carried when we joined the terminals was the charge for the fact that it was in series and was broken now? Then when we joined the light terminals, the total charge due to joining the light terminals became 266. Is it audible? And then if that total charge due to 266 is the charge from that our series at that setup, we don't know the voltage we have at that point because we joined it. At the point where we join the two together, we don't know what voltage we have in that connection. Because remember when I told you that voltage that you have in a capacitor is simply what will charge that capacitor. So a situation where due to that, what's it called? Terminal that is connected, I am having 44.44. It simply means that 44.44 was already there when I brought that 266. Am I confusing you? Well, let me take it on the board and speak in English. Let me show you what I mean. I want to win. I have capacitors in parallel. And initially I don't know what voltage I have, but it is connected. I have minus plus. This is 4 microfarad. This is 2 microfarad. Now, if this be the case, you will notice that at this point where I am bringing the light terminals of this and the light terminals of this together to be joined, to be connected, the charge I have on this is not as a result of it being in parallel. The charge I have on this is not as a result of it being in parallel. It's as a result of it being in series. I'm bringing that break up. That setting that I had to carry from series together. And when I bring it to be in parallel, it is no longer going to be in series because charge in series is the same. While when it's in parallel, it's different. But this time I'm joining these two. So when I combine these two things, it's simply going to give me a total charge of 266.66. Baby? Yeah, that is what I brought in. The voltage here I don't know. But voltage is always the same. So if the voltage is the same, that means that I have to find this voltage. What am I going to use in finding the voltage? Is simply the charge in the capacitor that was broken from capacitors in series. That's what I'm going to use to find this voltage. The minute I find this voltage, I'll now be asking myself, now that I have a voltage, this voltage powering this capacitor, what will it be able to do for me? To give me a charge here and give me a charge here. The minute I find the voltage from the charge I carried here in series, and I get this, I'll now be asking myself, this voltage, what work can you do for me in order to store something inside 4 capacitors and 2 capacitors? So that is the reason why the minute you get this, easy to find this, you are now finding what charge will be here if this voltage that is here happens to power this and power this. So first of all, we have something coming here. That works with our circuit to give us voltage. We are now looking for what this voltage is. The voltage helps us charge the capacitor now. It's not like we have a voltage that already charged this. This is going to help us charge this in parallel. So please, when you are thinking about this, think of it in this order. This comes in to get you what voltage is actually here to go to. And this voltage powers, charges your capacity. I don't know if I've done justice to it, but as I'm talking, I'm still thinking of another way to put it so you understand it. So please, the brake is very important. Is in series. That brake is very important. That brake, you do not just carry a capacitor and come here. The capacitor you got here is a capacitor that has charge because it was first connected in series. That's the one I'm trying to do. And this capacitor that was connected in series, you need to find the voltage it will have when you join the right terminals. Once you get that voltage, when you join the right terminals, you now need to ask yourself, what will this voltage be able to do now on these two capacitors and these four capacitors? I think if you don't understand it up to this, when you read over and over, it should make more sense to you. It should. I ask, what is the question? You see what? Just be talking, I can hear you. Even if you choose negative or positive, the value will be the same. It will not even carry minus. Have you ever seen where somebody wants to write proton or electron, and the person will come and say 1.602 times 10 raised to the power minus 19 proton minus 1.602 times 10 raised to the power minus 19 electron? And this is something like that. You don't show this charge. So when you are joining that circle, you don't show the charge. You don't show the charge. What you just say is that it's a positive. The charge of proton is essentially the charge of electron. So with that said, I believe as we progress more, if you see more questions like this, it will help us be thinking. When there is a break, you don't discard the charge. That's what I'm saying. When you hear something was connected and then move to be connected in another way, whatever charge you have here must be carried into that circuit to do something here. Must be carried into that circuit. But because of the fact that the voltage connection here and that of the other one is not the same, this voltage will do another work, a different type of work. And the work it will do is a work that goes the same to the capacitors. To do a different, the other one was doing a different work. This voltage will do a different work. So the problem here is simply on the voltage. That's why I'm stressing. Here we're having stress on this, understanding that the voltage does work done in carrying charge. So once the setup is not the same, the voltage will do a different work. And that is why you have that slight confusion. They said, explain with diagram the action of dielectric in improving the qualities of the capacitor. I've given you this diagram, so I'll not draw it again. I've given you this diagram. When we started, I gave you a diagram for action of dielectric, where we say plus, minus, minus. So let's move to the next one. Then how it does improving and the rest, I've shown you too. I said for voltage, the dielectric decreasing, voltage increasing. Voltage decreasing, dielectric increasing. I've shown you that one. So let's solve number 3b. Let's solve number 3b. They said if a 120 picofarad capacitor is charged to a potential difference, I can clean the board, right? Then how is your mom? It's fine. Is it up to 4? Is it up to 4? Is it up to 4? Chimamaka, today that you made mistake to come to Victoria. Today that you made mistake to come, because I know you got not even talk. You come once in a blue moon. Why if you say eat before morning, you will not eat. Always eat before morning. I keep saying it. You say what? You wait for lectures. So food in your stomach. Food in your stomach left with the lectures. You are trying. Okay. We will soon be through. Sounds good. The capacitor is just a potential difference. So a potential difference of 120 volts before connecting it to another capacitor. Calculate if a capacitor. Okay, thank you, bless. If a 120 picofarad, sure you see why I said always come to get with them. Because sometimes I'm seeing it, but I'm not writing it. So calculate the capacitance of the second capacitor if the potential difference across it is 80 volts. The 120 picofarad capacitor is charged with a potential difference of 120 before connecting it to another capacitor. Calculate the capacitance of the second capacitor if the potential difference across it is 80 volts. So the first thing you do is to write solution. Let's solution the answer. Can I get it? Solution. So once you write solution, you bring out everything needed for this. So I have this diagram will help you a lot. Me, I don't think you can solve this without using this. If you try to solve it without using this, if you've done it for so many times, you'll be able to get it, but it will take you longer time. So the easiest method is to always apply this. And always remember that every connection, even if they said it before it was broken, every connection does something. If you connect it, it does something. If provided that there is voltage there. If it charges it, unless they said it is uncharged. But once you get connected, you are expected to know that it was charged. So if I have this, if I come here, I can remember that Q is equal to C. And because it's just one capacitor I have, I can just say that Q here will simply be equal to capacitor here is 120 picofarad. Shall you see? Yeah, I can say another thing. Okay, if you want, you can convert your lesson of that times 10 raised to the power minus 12 times 120. Why I'm converting it? Because it's just 1 half. No other one to tell me that. But if you want, you can still use this. Once you want to work with 1 point. Like this. So columns because we convert it. So our charge in columns. That's our charge in columns. So notice something. It is a capacitor is charged to a potential difference of 120. So we've written that one, we've shown that one. Before connecting it to another capacitor, we need to show that part. The problem now is that they use the before to cancel the full stop that is supposed to be here. So it's still the same thing. I said always take each full stop. So before, so the next part, which is the B part, every capacitor question, if you are not using this mindset, you'll be having issue with it. Sometimes when you solve, you will get answer, but your answer will not be the same thing to what should be. So now B will be equals to, let's do, this is the 120 here. The wire, not say the 120 change. Before connecting it to another capacitor. 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 Calculate the capacitance of the second capacitor. If the B across it is 80 voltage. Now see something. How do you know if the setup is in series now or in parallel? Yeah?
The voltage are not the same.
The voltage are not the same. Okay, so that's why it's in what? Well, yeah, you are the one that sent that one. Another try, you try. Another one. You try. Any other answer? But see, let me tell you. Initially, this is minus now and plus. So it was charged by 120 volts. Then before connecting, this is the same thing as saying it has been charged. It has been charged. That means before it was broken. So that means this voltage is now removed. And when this voltage is removed, it is now connected to another capacitor. The voltage was removed and it was connected to another capacitor. So this 8 that you are looking at, is simply the same as saying we have a charge on this one. We have a charge on this one. This is microfarad capacitance. Picofarad capacitance. But this 120 volt is carrying a charge into this place, and the charge is carrying into this place is a charge of Q, which is 1.44 times 10 raised to the power minus 8 ohms. This is the charge is carrying into this place. And this second one, this second capacitance, we don't know it. So let's call it C2. So it is not connected. It was that other one, the voltage was broken. They now connected this. So for the fact that a voltage was removed to connect a capacitor, automatically that's the first signal that is in parallel. That's the first signal. Then the voltage across the connection. See, calculate the capacitance of the second capacitor. If the potential difference across it is 80 V. So which means that as I remove this, we're going to be having remember, somebody wants to tell me what is it not in the second capacitor that they said 80 V? If you say it's in the second capacitor they said 80 V, I don't disagree with you. But what I want to ask is, where is the second capacitor connected? It's connected to the first capacitor. So if that is the case, I am having 80 voltage. So please, the point I'm trying to make is the series thing might want to confuse you, but where you should be paying attention is, was there a break to connect a capacitor? If there is no break, assuming they want to connect this without, assuming it's in series, without telling me, what they just tell me is that I have another capacitor joined to it. They won't have to indicate that it was charged or anything. So, provided I have to connect a second capacitor, I have to break this. That's just what I'm saying. And if I break it, I can't break this. And then after I've broken it, I am going to start saying I am putting something here. I can't break this. After I've broken it, and I start putting something here. So now I come and put it. So it's here I have to break to do that capacity. That's the point I'm making. And that's how physics is built. So if I have this now, what I will simply do in this case is to just say, what is the charge here? The only charge I have here is this one. Share you. I told you don't dump charge. Notice the idea I am using. Each one should have a concept you are taking note of. The idea is that if there's something before something, that charge you got there, you always carry it, you don't dump it. So I'll simply say, remembering that Q1 plus Q2 is always equals to C1 plus C2, then voltage. If I have this idea in mind, I can now call, let me do this with copy this now. Voltage for parallel is always the same. I can now come and do this. I'm going to be having Q1. My Q1, the Q1 is 1.44 times 10. This one minus 8, Chevy. Column Chevy. But that's the only charge in that setup. There is no charge in Q2, it's uncharged. You don't know the charge. So I can't say the total charge is just this. So I have this is equals to my C1, C2. I don't know C2, but I know C1. So I have 120 plus C2. The voltage is 80, Chevy. 80 times 120. 9,600. Wait, and the 120 is supposed to be before 5 because we converted the other one now. Sure, you know, we converted the other one altogether. So it's supposed to be 120 times. It's supposed to be 120 times 10 is minus 12 plus 6 equals 8. I have watched it again. 9.6 times 10 is plus, here, go here, 86 which is equals to 1.44 times 10 raised to minus. There's an idea that makes, when you see a question, even as you are solving it, you already know what to expect. And that is the idea that I'm telling you. Those things I normally say, anytime there is a break, you must solve something about that setup first before the break. And when you solve, if you hear that there is a new connection, you must carry whatever you got for break, discharge or anything, to the new setup. Those are ideas that must be here before you are solving it. And whenever you hear that something was connected and then charged and then broken, and you are now having a new capacity, you must know that that setup is going to be in parallel. These are ideas that once you have, you already know what you should expect. So those are the things that you have highlighted. I want you to pay attention to. So notice that this is now looking like where I can collect items. Because this one is only C, this one is not having. So I can say 1.44 times 10, this one minus 8. If this crossover to minus 9.6 times 10 raised to minus 9 equals 80 C2. Our bunch will be up there. So you know why I'm doing this thing now? items upon what you have a gun. Mine there, remember. Mom is there. Mine is there. There. Where's your mom? What's that your son in the mind? It's not Austin, yes. Austin. You see Austin? There's a people. There's a man. It's a man. Because in soccer people like answer. Are you from the soccer? Now, biology took BSK is so, so 4 points. Nice. Next one minus 9. It was 80 C2. So now to make C, that is the capacitor. Capacitor. So find the second capacitor for the C2. If I go size by 80, I want from C2 to now because 6 minus 11, which is going to be in farad. Is this 6 times 10 minus 11 equals in farad? So let's check what we have here. Okay, they got their own in picofarad. It's still the same thing. Hope you know that 60 is the same thing. Sure, you know that 60 picofarad is the same thing as 6 times 10 minus 11. So we are still having the same thing, so we are correct. So we did not convert it. So let's check for the next question. Let's look at the last one. Let's look at the second. Second to the last one. No, the last one actually is very simple. So we'll do this one second to the last one. Ask. Charge. Yes. If you don't know charge in a particular capacitor, it means when you already have a charge that you are carrying into that circuit, it means that that second one is uncharged. A capacitor can be uncharged. But we know that the idea of capacitor is simply to store charge. So a capacitor that you are carrying from a particular circuit, maybe a circuit was broken, into another circuit. In that case, if it was not indicated to you that that capacitor is having any value of capacitance, let's say you have 2 microfarad, assuming I have, for example, here, let's say I have here 2 microfarad, automatically the charge here will simply 30 times 2. Sure you know. But in this case, we don't even know the capacitor. We don't know the capacitance. So now that we've gotten this capacitance now, if we are to find the charge here, it will not be easy for us. Because we can now simply say, this thing now, times this thing is the charge here.
But I think that when you respond to this, net charge is equal to net capacitance.
Net what?
Net charge is equal to net capacitance.
Please, I want you to open your mind in what we are doing here. Don't just ask me by assumptions. Look at what we are doing, actually, what we are doing here. What are we doing here? If you even do by net charge or net capacitance, what is the capacitance you have? Do you have any capacitance for this thing? We don't have any capacitance here. The only capacitance we have is this one.
We have a
It's when you've gotten the value, you can now look at it and say that you don't know it. At this point, you don't know it. In fact, at this point, what we have is a capacitor that we don't know. So you can't solve anything with it. The only time you say a capacitor is charged is when it is indicated that it's charged, or when you are giving the capacitance and the voltage. In that case, you can now easily do the capacitance here times this voltage. You get it? A situation where, let's do it this way now. Let's say we are here, and we come here and do Q here will equals to C2 times 80. What would be the charge now? You see that we don't know it. Because we don't know these two. We don't know this, we don't know. Anytime you don't know two things in mass, there is problem. So for that reason, this cannot go. So the only way to know it, to not stop, is to simply tell yourself which one has charge. And the only one having charge is this one because of the fact that it was in the setup before joining this. So as you are mixing what I said, always like look at the cases. This is a case where there is no capacitance. No case of no capacitance. Another case where you can have this kind of thing is when they say one is charged, the other one is uncharged. So two things to take note of. When it says uncharged and when you have no capacitance, the charge you must use is the charge you are carrying into the circuit.
One is in minus 10, and like people correct minus 10 is the answer. But when 120 is minus 12,
Come again.
is 60 picofarad, but it's 120 picofarad too. Now 60 picofarad, 60 times 10 raised to power minus 10 farad, and then 120 goes 120 times 10 raised to power. See the answer.
Yes.
Yes. Yeah, 6, but if we convert it to 60 times 10, okay, 6 times 10 minus 11 farad. Okay, it's bigger. Why is it not like 12? It's 12. Okay, now you're 120. Look up, you see 120. 120 times 10 raised to power minus 12.
Okay.
Get it? I'm not asking why it's
See. Do something for me. Do something for me. Let's check something. This is 6. Shall we? Times picofarad is what? Shall we? Yeah. This is pico, shall we? This is presented as 6 times 10. This is just power 1. Times 10 is power minus 12. You see? This is now 6 times 10 is power 1 minus 12. It's well. It is well. In Jesus' name. Alright, let's go to the next one. So the next question is number 4. They said, okay, you see number, yes. You explain how variable capacitors can be made. I've told you to go and check that out using rotor and pseudo. You said there are capacitors whose capacitors are not stable, they are not constant. They are made mechanical in such a way that the capacitors can be adjusted. I told you to go and research on it, we need to research it. So now the question here says, a capacitor stores 120 kilowatts hour. Kilowatt hour. Yes. 12 kilowatts hour. Energy. When it believed there is a potential difference across it is 1,500 joules. The answer estimate, because try and do this one. Estimate the capacitance. Try quickly to do this one. Side of both. Try to see if you can do this one. Can you help us and solve on the board? Try. Push yourself.